But tonight I'll now hand over to our speaker, Dr. Ryan King.
Okay, thank you. I'll introduce myself in a minute. Obviously, you had a talk recently about autonomous vehicles, and I can gather.
3 autonomous vehicles.
Or autonomous cars, perhaps. There are autonomous cars or vehicles for getting you home from the pub when I was a kid, because where I grew up, near Heathrow Airport, in a little village called Iverheath, there was a pub just at the end of the road in which we lived. And there was a guy who used to go there. Every Sunday he would go there, and he would drink himself until he could barely stagger. He would then come out of the pub, climb into his vehicle, but his vehicle was a horse-drawn cart, and the horse knew perfectly well where he lived. So he would climb up in, he would just about be able to give some signal to the horse. He would then slump, comatose, in the seat of this cart, and the horse would just clop, clop, clop off the road, and I presume knew exactly where to go all by itself. So that was about 45 years ago, and I guess, you know, we're just getting round to autonomous vehicles to get us home from the pub. So I'm Brian King, I'm from the Oceanography Centre here in Southampton. This was me in about 2002 doing some field work in the Indian Ocean. We were very excited to go. And we were beginning to deploy some of these yellow tubes, floats in the Argo programme. And Argo got its name as a means of measuring the ocean that corresponded to a satellite measurement system that was called JSON. So we decided we would call ourselves Argo. We did once upon a time force it to be an acronym that stood for something, but it was so artificial we just dropped it. We just call ourselves Argo. So Argo, a fleet of unattended instruments to measure global warming. There will be, knowing that the audience here would be a mixture of people with a background in science, perhaps people who have no background in science but are just interested in science. There will be quite a lot of graphs for those who like those sorts of things, but understanding and following the point of what I'm saying will not depend on looking at the graphs. So if graphs aren't your thing, you can just rest your eyes for a moment when they come up, but if they are, there'll be enough in there to get some sort of meat into it for those who want it. So what I'll talk about a bit, what is Argo for, why has it been invented, who's doing it? We'll have a bit of the context of global change. We're interested in global change and measuring global change. The importance of automatic platforms, robotic platforms for ocean exploration, because the kind of measurements we want to make, you just can't have enough people in the right places all the time. So you've got to do it with instruments that measure when you're not there. Why has the Argo program revolutionised global ocean observing? What are we learning from it? There'll be some indications of the sort of scientific research that we're doing at the moment with the new measurements, and something about what the future holds. Global change. Here's a picture of a glacier up in Spitsbergen, up in the Arctic. You probably can't see it very well. Here's the glacier as it was seen in 1906. Here's the outline of the glacier. The same view in 2005, all the mountains are the same, the lake is the same, the glacier is just completely gone. Lest anyone should imagine that global change is not seriously happening. And even if you said, well, it's just a bit of a cycle where it didn't snow very much, that'll take several thousand years, even if it started snowing tomorrow, to build up again. So we think that things are changing because of the greenhouse effect. The greenhouse effect has always been with us. It's been a very important part of making this planet habitable. Without the greenhouse effect, we would be a frozen waste and there would be no people here. So briefly what it's about, many of you will be familiar with it. The idea is that you've got the layer of atmosphere. Sunlight comes in and can pass through the atmosphere rather easily. When it then gets mixed up and reabsorbed as heat, the heat doesn't get out quite as easily as the sunlight comes in. So that means because of the atmosphere, the Earth is a lot warmer than it would be if there was no atmosphere. If you go to the moon where there's no atmosphere, then at night time it's about -70 or thereabouts everywhere, just because there's nothing to keep you warm. So the atmosphere and the greenhouse effect was tremendously important. What's happened as we've put more carbon dioxide into the atmosphere is we've simply made that greenhouse effect a bit more effective, and that's what's causing the warming. So, would anyone care to hazard a guess as to when the first proposal was made that increasing atmospheric CO2 would lead to global warming? When you imagine people first began to get the hang of that notion, they understood that the greenhouse effect was there, and they thought, if we start burning all this fossil fuel, we will cause global warming. Anyone want to hazard a guess? University challenge, I'll accept an answer within 10 years of
1850.
1850, a bit later than that. That's not a bad guess. That's not a bad guess.
1950.
Well, the greenhouse effect was well understood in the first half of the 19th century. So the scientists then understood that light at different wavelengths passed through gas more or less easily. By 1859, John Tyndall, a great guy interested in climate, had measured the properties of specific greenhouse gases. He measured the properties of carbon dioxide and methane, the constituents they knew were there. So it was known that this was important for maintaining the planet at a habitable temperature. In fact, the first suggestion, the realisation that industrialisation and burning of carbon dioxide might start causing problems. A Swedish guy, Arrhenius, he got the Nobel Prize for Chemistry in 1903, and in 1896 he considered that if you doubled the amount of carbon dioxide in the atmosphere, and he figured out in 100 years we could do that, mankind could do that, he predicted a 4-degree rise for a doubling of CO2. So that was 1896, was the first suggestion. It was just a theoretical suggestion at that stage. It was one of those wonderful things where the theory preceded the ability to actually measure it. Of course, when you add carbon dioxide to the atmosphere, lots of things change. So this is a highly complex picture, you don't have to understand it at all, and it's really to remind me to say that when you start producing global change, there are changes in what we call the cryosphere, the ice system. There's snow, frozen ground, sea ice sheets, all those things start changing. There's changes in the ocean, of course, which I'll be talking about a bit, changes in the ocean currents, in the sea level, in the animals and plants that live in the ocean. There's changes in the atmosphere, there's changes in what we call the hydrological cycle. That's the fancy name. Water evaporates over the sea and falls back on the land, and where it falls back and how fast that goes round, we call that the hydrological cycle. That will change, clouds will change, lots of things will change in a complex way as we start tinkering with the planet. So here is one of the most famous pictures in climate science. It's the graph of the increase in carbon dioxide in the atmosphere as measured at the top of a mountain in Hawaii, on the top of the Mauna Loa Observatory in Hawaii. And it started in about 1960. A guy said, oh, I'd really like to know how that varies over the course of a year. So he went out and he made measurements every day for a year, and he discovered it went up and down in the course of a year. As the temperature changed, the amount of carbon dioxide went up and down. And then his manager said, well, you've done that now, you'd better come home. So he said, well, perhaps I'll do it for 2 years, just to see. So he did it for 2 years, and then he thought, I can tell it's gone up. So he thought, I'd better stay. And fortunately, the people in charge of his funding said, well, all right, you can stay for 5 years. So he stayed for 5 years, and actually, the series has gone on now for 60 years. And this is the history of the increase in carbon dioxide. The red line is pretty much monthly measurements, and then you can see it goes up and down with a seasonal cycle. Every year it goes up and down, and every time you come back to the same month, it's higher than it was before. And it's recently passed this number of 400. So when I started my research career back here, the number was about 360, and people said it'll be 400 soon, and he thought, no, it'll never be as high as 400. But if you just keep burning coal and oil, the amount of carbon dioxide just goes up. So is 400 a high number? Let's see. So this is a series estimated from about the last 10,000 years. So people say ice ages have come and gone, carbon dioxide has come and gone. So it's estimated what the carbon dioxide content was back 5 or 10,000 years ago. This is clever stuff. They drill out ice, they drill down in the ice in places like Greenland and Antarctica, and the ice has got little bubbles of air trapped in it. So they can extract the tiny bubbles of air and measure how much carbon dioxide there used to be. And it used to be about 260, between 250 and 270, and it's gone up and down for sure. And then when you start getting to about 1800, it starts going up seriously, and when you get to the last 50 years, it's gone up really seriously. So if anyone, you don't have to be very smart in science and engineering and technology for anybody to say, yeah, it just goes up and down. It's always gone up and down. There have been ice ages every million years or so. It's gone up and down. This is not a natural variation. This is the sort of rate it changes over a few thousand years. This is not part of a natural variation, I think we can safely say. So, just a sort of reminder of where all the carbon dioxide comes from. So, over various years, this is the amount of carbon dioxide being emitted and stored in the atmosphere, and the colours indicate different sources. So, the big pink slab is the burning of fossil fuel, so the burning of coal, oil and gas. Various other slabs a bit smaller. There's a contribution of the increasing carbon dioxide comes from deforestation. The equivalent amount in terms of global warming comes from methane. There isn't very much methane, but it's much more effective at trapping heat. So there's the methane segment, there's nitrous oxides, there's other gases. And what sort of uses are those put? This is a global average of how that energy is used. In different countries it's different. So across the world as a whole, about a quarter of it, the blue sector here, is ordinary energy supply to domestic homes. There's a big red one here is industry, there's agriculture, there's forestry and so on. In different countries this would be different. So in Australia, I was talking to an Australian colleague, he said in Australia 90% of the carbon dioxide is related to static power, because they've got a lot of industry, a lot of air conditioning and not many vehicles. So solving vehicle transport in Australia is not that big a deal, because it's only 10% of their carbon dioxide problem. Their big carbon dioxide emitters are industry and what he calls standing power, stationary power. So it's different for different countries, and what different countries need to do depend on your population, how big the country is and all that kind of thing. So what's the effect having? If people want to sort of move through and sit down, I'm not fussy about people moving around as we
There's a sort of bench made out that table over there.
Oh, right. Well, there's a seat. There's a couple of seats as well. So this is a graph, which again, all you really need to be able to recognise that it goes up towards the right. This is a graph of global mean temperature. Now, when people talk about the global mean temperature, they kind of mean the global mean air temperature. Everyone around the world measures the air temperature where they are, and then you average that together. Now, I'll point out later on, this is not a very good way to measure global warming, but for a couple of hundred years, that's the best we have, because people have measured temperature for quite a long time. And if you sort of look at the last 150 years, you'd sort of see, you'd say, well, it's going up according to this red line. If you looked over the last 100 years, you'd say the trend is the blue line. If you look over the last 50 or 25 years, you'd say the trend is the yellow line. So the point is, the rate at which warming is happening is getting faster and faster. For the first 100 years of industrialisation, it was rather slow. Now it's rather faster. And it's about 1 degree every 6 decades or so. So about a degree per 60 years is the rate at which we are currently warming our planet. So this is almost done with the preamble. So where's this going? What might happen? So this is a graph from the most recent assessment by a group called the Intergovernmental Panel on Climate Change. This is a group of international scientists who get together and try and say, what is happening to climate? What is the best evidence, the best hard evidence? So they gather the evidence of what's happened, and then they get the best theoreticians to say, what do we think is going to happen? And there are 3 predictions in this graph, which relate to different possible scenarios, as they call them, for how emissions and carbon dioxide might change. So if we just carry on emitting at the rate we are, they say, well, it'll go somewhere up this red curve. It'll be, sort of between the yellow bands. We're not quite sure. There's a bit of uncertainty, but it's going to be up there. And in 100 years' time, it'll be a couple of degrees warmer than it is now. Then they say, what happens if we sort of curb our emissions and there isn't, and the atmosphere stays about how it is now? Then you get the grey curve and these black curves and say, well, it only goes up slowly if you do that. Then it says, what happens if you stopped emitting altogether? If you could just suddenly go to clean power tomorrow? And curiously, that has a sharp increase to begin with, and then it gradually, over the next 200 years, sort of recovers. And this little curiosity here is because if you have chimneys burning coal, not only do you put a lot of carbon dioxide in the air, which traps the heat, it also puts a lot of soot in the air, which actually acts as a bit of a shield, a bit of an umbrella. It stops the heat getting through if you get a lot of particles in the high atmosphere. So if you went to 0 emissions, the first thing you'd see would be a little bit of warming, and then it would gradually tail off. So depending on how governments decide to do things, we might be up here, we're very unlikely to be down here, we might be somewhere in between if they start seriously getting on top of the CO2 problem. But certainly the unconstrained emissions carrying on as we are, you'll end up damaging the climate really very profoundly. So it talks about, well, perhaps 2 degrees in 100 years. None of us are going to be around in 100 years' time, I don't imagine. You know, children, grandchildren, great-grandchildren might be. Does 2 degrees in 100 years matter? You might say 2 degrees isn't so much. The problem, of course, this is the average over the globe as a whole. And the people who run computer simulations and predictions can say, well, where will that warming happen? And the answer is, nearly all the warming in terms of the air will happen over the continents, because the oceans will keep themselves relatively cool. The continents might have 4 or 5 degrees of warming, because there's nothing to keep them cool. So this is really very much more serious. If people say, oh, we're aiming for a 2-degree cap, on the United Nations says 2 degrees is the maximum we should have, 2 degrees does not mean 2 degrees everywhere. It means 4 or 5 degrees in some places, and a lot less in others. So, getting round to what I do, the importance of the oceans. So the oceans have absorbed around about 25% of all the anthropogenic carbon dioxide released into the atmosphere. So of all the carbon dioxide burnt and released in coal and gas and oil, about a quarter of that is already in the oceans. So it's pretty important that the oceans carry on doing that, because if they didn't, we'd really have runaway warming. And we study carbon in the oceans very seriously, and that's a completely different topic of research. And at least 90% of the extra heat has been trapped by atmospheric CO2. Is also in the oceans. So the oceans are tremendously important at capturing nearly all of that heat and burying it away. And if the oceans weren't doing that, boy, we'd have a serious problem. We'd be a lot warmer. So the project that I'm involved in, this Argo project, is about measuring things in the ocean and trying to account for that 90% of heat in the oceans. So a bit of history. The importance of robotic platforms for ocean exploration. Throughout the history of oceanography, and oceanography started in about 1870 or thereabouts, so in about the last 140, 150 years. If you want to measure the ocean, you've got to be there on a ship. And the first seriously planned and organised ocean expedition was on a ship called the HMS Challenger. It was a 60-metre vessel, adapted naval ship. It was about a 2,300-ton ship, so relatively small, about 200 crew, of whom 5 were scientific researchers, the rest were Navy people to run the ship and make the ship work. So about 195 crew and 5 scientists. They were at sea for 2.5 years, and they collected 263 measurements of temperature. So about every 3 days they would stop the ship and lower instruments. They had the ability to lower instruments, steam-driven winches, into the ship. They collected 260 measurements in 2.5 years in the Challenger. In the 90s, when I started my career, we had something we grandly called the World Ocean Circulation Experiment. We had purpose-built research vessels, typically 3,500 tons, 25 crew and 25 scientists, so the number was now more or less balanced. And over a 10-year period, we collected 10,000 profiles of temperature and salinity. We measured the ocean in 10,000 places over a 7-year period between us. With the Argo program, since 2004, the Argo program, its length is 2 meters, its weight is about 0.03 tons, and it has 0 crew, and we collected 1.3 million measurements in about 12 million days of operation of our equipment at sea. So it has revolutionised measurements. With these instruments, you can do things you simply couldn't do with ships. It's not that they replace ships, it enables you to make measurements you could not otherwise make. So what are the origins? The idea of one of these floats, I was hoping to be able to bring one, but all the floats recently been packed up on ships to deploy at sea, so I was not able to bring one to show you. If I just go to the next picture, this is what one of these things looks like now. Being deployed on a ship, it's about 2 meters long, it's a tube, and it drifts around and makes measurements. The idea of one of these floats was first developed in the mid-1950s by an American oceanographer had realised that it would be a really good thing to do to have equipment that could just drift around in the ocean and sit at a particular depth in the ocean, park at a particular depth. But it was widely understood that this was not possible, that the engineering did not permit this to be done. A guy called John Swallow, who was a British marine scientist, had come in from outside the field. He'd come in from other fields of engineering. He hadn't heard that it couldn't be done, so he did it, because he was unhampered by the notion that it could not be done. So he simply thought about how to do it and was able to do it. So the first floats that he built, and this was in our predecessor lab up in Surrey, which is where I started my career. Basically, the pressure cases were aluminium scaffolding tube. So long tubes, long aluminium tubes, you can see him laying some out here, 3.5 meters long, bunged up the ends, put in some batteries, put in some sensors, and they contained a sound source that was tracked. So no satellite navigation in those days, they would emit a sound source, and if you sail around in a ship, you could listen to the sound sources and triangulate on where they were. So that was the origins. These days, we have equipment like this, and I shall explain what's inside the tube in a minute and how it works. And we have the Argo program. So what is the Argo program? It's a network. At any one time, there's approximately 4,000 of these floats that I showed you, deployed since about 2000. By 2004, we had some everywhere in the globe. By 2007, we reached our initial target of 3,000 of these operating worldwide. Each float is a self-contained component of the network, so each one stands alone. It measures ocean temperature, salinity, which is important for measuring ocean density, and the currents, the ocean circulation. There's about 30 contributing countries, which are kind of the usual suspects. If you said to yourself, who would be likely to contribute to a big maritime project? In Europe, it's UK, France and Germany, Canada and the USA, Australia, Japan, Korea, India, are the usual kind of countries you'd expect to bear the brunt of it, and about 25 other countries that contribute in small ways. So this is a picture from the beginning, me in an earlier time, posing with a float before deploying it in the Indian Ocean in 2002. So what's inside the tube? Typically, the thing operates by having a small bladder at the bottom. So if any of you are familiar with scuba diving, you have a buoyancy control jacket. You can pump air in and the diver comes up, you can let the air out and the diver sinks. So you've got a little rubber bladder. We use hydraulic oil rather than air because we have to work at very high pressures. When the thing is at 2 kilometers ocean depth, it's 200 atmospheres pressure, so air won't do the job, you're into hydraulics. You've got some sort of hydraulic pump. This has got a long lead screw which just pumps a ram down to pump oil out into the bladder. You've got batteries sandwiched around the side, and you've got an instrument payload up at the top. And inside you've got some circuitry, and at the top you've got a satellite antenna because you use satellite comms to get our data back. The float weighs about 30 kilos, and you've got about 280 grams of reserve buoyancy to get you up and down between the surface and 2 kilometers depth. So the engineering considerations are considerable. You've got to load you've got some batteries that you can load on board, and that's got to give you 5 to 8 years lifetime for buoyancy change, payload instrument, powering the payload, and getting your data back by satellite telemetry. So you've got round about 30 D cells in which you can there's your energy for 5 years operation. So how is Argo revolutionising our global observations? Well, Argo came along because we realised that technology will enable us in a cost-effective way to do something really quite extraordinary. At the moment we're measuring temperature and salinity. In the future we'll measure not only TNS but dissolved oxygen, nutrients, ocean acidification, biological parameters. And what a float typically does is each one of these floats, each one of these dots in that map represents, as of the 8th of October, so that was as of yesterday, I downloaded yesterday's map today, each one of these dots represents one of our instruments reporting data and making ocean measurements. So every 10 days the float will, starting a cycle at the surface, it will sink to some predetermined depth, usually 1 kilometer down. It'll then drift for 9 days. It'll then dive to 2 kilometers, rise to the surface, and broadcast its data back by satellite. And each one of these dots will repeat that cycle every 10 days. And it's this rise from 2 kilometers up to the surface where it measures the temperature, which are these critical measurements that we want to make. And each one of those dots, somebody had to build the float, they had to go out, they had to put it in the water, and we have to process the data from it. So we've got 3,787 active instruments at the moment. It's been as high as 4,000. The instruments have about a 5-year lifetime, so they begin to die off, and we have to keep replenishing them as fast as they're dying to keep the numbers up. So there are lots of different designs. They're all rather similar. All the 2 kilometre floats are rather similar. They're all tubes with satellite antennas at the top, and different engineering companies have solved the problems in slightly different ways. They've all got their buoyancy control at the bottom. They've all got their sensors on the top. And as I say, here are the dots. So this picture shows how the array grew in numbers. You can't read the numbers, but in 2001 it started with none. It reached 3,000. It's hovered between 3,000 and 4,000. Here was about 2007. So up till then, we were putting them out faster than they were dying. And when the number got large enough, then they start to die as fast as we put them out, and the number basically tails off. So this map, this movie, will show you the growth of the float. So every time a new dot appears, that means we went out and we put floats in the water. Where a row of dots appears, that meant a ship went out and kept deploying floats once a day, or as it was crossing the ocean. And you'll see the tails are the last 3 months of the float's life. So the tail indicates where the float is going. There's a little clock that goes round here, and each once round is a year. So let's see if this plays. So early on, you'll see a row of dots goes across the Indian Ocean. That was me in 2002 when the posed picture was. Here we go. Any minute now. There went the ship, and we put out 25 floats. So we're up to about 2002 now. By 2003, we finally painted in the South Pacific, and we had floats kind of everywhere, so we could begin to get a global picture of what the global average temperature was. By about 2000, where are we now? We're just coming up to 2007. By now, the array is more or less up to strength. So for the last 10 years, we've had consistent global measurements, going to make serious statements about what the average ocean temperature is and how global warming is going. And you can see many of the standard ocean currents are there. All the ones in the southern hemisphere or on the Antarctic are going to the right. That's because that's where the prevailing currents and winds are. That's why the big ocean racers always sail clockwise around the Antarctic. You can see in the equator, lots and lots of currents go back and forth, mainly east-west, and it's a lot of fun. So, as I said, Argo is revolutionising global ocean observations, and there are many things that, having it done with autonomous vehicles, make us able to do things we could not previously do. So I said, the first 3.5 years was the Challenger map. This is where the Challenger went, and that was the sum total of serious marine observation up to that era. These were the network that we did. I said it took us 7 years to get round all these lines once on ships. So that was people and ships, and we got round all these lines once. So we said, once we know pretty much what the average ocean temperature is. And the profiles cost about £7,000 each. If you take the cost of the ship and divide by the measurements you make, it was about £7,000 per measurement. In 1 month of our float programme, we've collected 10,000 more measurements. So this was 7 years. In 1 month, we've done 10,000 more at a cost of about £200 each, because the cost has just come crashing down, which makes it feasible to do this now every month rather than once every 10 years. But there are other aspects of what we've done. So this is a picture where this is the whole history of ocean observing up to about 2010, summarised in this picture. And what we've done is each 1 degree square, we've divided up the globe into 1 degree by 1 degree boxes, and then you count how many observations there were in that box. and then you put a coloured dot in that box depending on how many observations there were. So if it's white, that means there were no observations. That means at no time in ocean observing was there ever a ship here or here or here to make observations. Blue is less than 5 observations in the entire history of ocean observing. So in most of the world, there have been less than 5 in the previous 150 years. That is not very good for trying to determine how the planet is changing. And then you get up into the yellows and the reds, and you can see around the North Atlantic pretty good, the North Pacific not bad, particularly near the land, Southern Hemisphere, huge gaps. So, where it's white, no observations ever. There never was a person in a ship went there to make some measurements. If you now look at the first 10 years of the float programme, coloured in the same way, this is what the picture now looks. So apart from the very high latitudes where it's ice covered and our instruments don't go, you can now see, even if you can't see clearly, pretty much the entire globe is yellow and a lot of it is pinks and reds, which means in the last 10 years we've been making 5 or 10 or 20 or 50 measurements everywhere. So now we can actually see what's going on. And not only have we been to make measurements there, is happily our floats don't mind bad weather. So here is an illustration of the difficulty of making measurements in winter. So of course the ships that we operate out of the Oceanography Centre here are tremendously expensive. So they tend to only send them somewhere where there's a good chance of being able to do any work. They will not let us go to the Southern Hemisphere in winter, because they say you'll sit there for a month and do 2 days work and 28 days sitting out in a storm. So they don't send us there in winter. So here is, for 50 years, the entire sum of August measurements in the Southern Hemisphere, and you can see almost all the Southern Hemisphere has never been observed in August. That's 50 years of conventional measurements. Here is 5 years of August measurements with the new floats, and you can just see we can now measure winter, summer, everywhere in the world. We can actually do the job. We can actually address these critical scientific questions of how is the planet changing. So, what aspects of Argo are so profoundly different from previous observing that it could be described as a revolution. It's not just an evolution, it is a revolution in how, in what our capability is. One thing we've done is free and immediate exchange of data from the research community. Now this may sound very obvious. You might think, well, if you make measurements, surely you should publish them. This was not commonly done before Argo came along. Researchers would go and they'd make measurements, they'd sit there, they'd be in their filing cabinet, they'd be on their laptop, and they simply wouldn't be instantly available. They'd be available 6 months later or a year later when you got round to sending them in. All our data become freely available within 24 hours. They come in by satellite, they go straight out on the internet within 24 hours. Unprecedented global coverage with good space and time resolution. I illustrated that with the maps that we've both got everywhere on the globe and all year round. We're making salinity measurements, which I shall mention the importance of the salinity measurements in a while. It's obvious that temperature is really important to know. The concentration of salt is also important to know, and I will get to that later. And the other thing that Argo successfully did was it agreed access to 200-mile exclusive economic zones through international brokering. Because there's actually a huge amount of important ocean is within 200 miles, and by default you're not allowed to go and make measurements there without special permission from the coastal state that you're within 200 miles from. You know, it's to do with fisheries and resources and all those things, but there is no automatic right to go and conduct research there. But through international bodies, Argo was able to broker permission for its measurements to be made, so basically a country has to opt out rather than opt in. And this was absolutely revolutionary. So a little about engineering, the engineering issues. Designing a float, the real problem is anybody could design one float that would work once, and it might cost you £1 million. If you want to make it really robust, you could design one that would do the job. The challenge is designing one that you can mass produce for about £15,000 or thereabouts. They have to operate for 4 to 8 years without maintenance. There's no getting them back. It's hard enough getting the ship to put them in the water. There is no chance of getting a ship to go and pick it up if it's faulty. So the mechanics and the sensor payload has to work for 4 to 8 years without maintenance. You've got to decide what sort of batteries, lithium or alkaline batteries. These days we use mainly lithium batteries. They're more expensive, they're much harder to work with, but they extend the lifetime of the float a lot. And getting floats out there is difficult. So we have lithium primary batteries, because they have much better energy density. You get more megajoules on board per kilogram of battery. You've got to think about the energy budget, which has to be split between buoyancy changes, data telemetry, and running your sensor payload. So again, your sensors have to be low power. It's not, you can't just take laboratory equipment that you can plug into the mains. You've got to think carefully about the electronics of your sensor payload. Lots of things you can't really use acoustics. You can barely use optics because those things burn up too much energy. So lots of passive sensor payloads. The sensors have to remain operational throughout the float life, so you've got to be able to put them on in the factory, and they've got to remain in calibration, working for 5 to 8 years, and you've got to be capable of data telemetry in all weather and at all latitudes. So you can't just use an ordinary mobile phone. So mainly these days we use iridium phones, and we get our data back by iridium. But you've got to be able to do that from round about a foot above the sea level in a force 8 at all times of year. So plenty of tough engineering challenges. What do you get for that if you solve those problems? Well, you get measurements down to 2 kilometres with a vertical spacing of every 10 to 50 metres. The pressure at 2,000 metres is about 200 times atmospheric pressure, so you've got to be fairly resilient. People say outer space is a harsh environment. The deep ocean is a harsh environment. Outer space has got cosmic rays, and you've got to have a lot. It's very difficult to get there. But once you're there, it's a relatively benign environment. The deep ocean is hundreds of atmospheres in a highly corrosive liquid. That is a tough environment to maintain your equipment in. Our floats are typically about 300 kilometres apart, so all those black dots, basically pretty much every 300 kilometres around the planet, there is one of our measurements. They operate on about a 10-day cycle. They measure temperature and salinity, as I said, sometimes oxygen. Other payloads are possible, but very constrained by the energy budget and engineering considerations, and you have no control over their location. They don't navigate, they're just taken wherever the currents take them, and you saw that movie that I showed. That's just where the ocean currents take the floats. Some of them are displaced by hundreds or even thousands of kilometres. So what can we do best? Systematic global coverage enables global problems to be studied. We've got a high data volume. We've now measured 1.3 million places. Deeper penetration than previous measurements in the past. Before floats came along, the mass measurement technology was temperature only to about 750 metres. No seasonal bias, so you don't have to worry about whether your measurements are biased by winter or summer. And we can get year-round, so we can measure on monthly, seasonal, annual, even longer timescales. So what are we learning from Argo? How are we doing on time? All right. Here is this carbon dioxide graph again, increase in carbon dioxide. The corresponding picture of increasing planetary heat is this picture here. Not be able to see the legend because it's not quite sharp enough, but what you need to know, so this is about from 1970 to the present. This is the increase in heat. It's measured in a snazzy unit called zetajoules. For those of you who like, mega, giga, and tera, and so on, zeta is times 10 to the 21. So this is the amount of heat that has been absorbed. All that heat trapped through the carbon dioxide, it's absorbed into the planetary system, and the 2 blue strips are the top half of the ocean and the bottom half of the ocean. The white is in the ice. The atmosphere is this little pink stripe, this purple stripe at the bottom. You can't see the purple stripe. If you get really close, you can. The atmosphere just doesn't contain any of the heat. In terms of the physics of the Earth's energy system, the atmosphere is irrelevant, almost. Of course, for agriculture, for you and me, we feel it through the atmosphere, so the atmosphere is critical. So we have to understand the atmosphere, but as a physics problem of energy going in and energy going out, and where is the energy stored, it's all in the oceans, which is why we have to measure them. So this is how...
Sorry, the dashed lines on that past image, what
Oh, yes, okay, so the DAS line, that's the uncertainty estimate. To begin with, the Earth's heat content had a big uncertainty back in the 70s. That's because the data were very sparse. What you notice is from about 2000, which is here, suddenly the dashed lines get much closer together. That's because suddenly we're actually measuring the heat content directly. We've gone out, we've measured the ocean temperature, we know what it was. So suddenly the uncertainty gets very small. So back here, you could have got away with saying, well actually global warming, not sure. You know, looks like it's about 50 of these zettajoules, but actually it could be anything from minus 20 to plus 100. Now, there is absolutely no doubt, it's absolutely unequivocal, that the Earth is warming up, and we know exactly what rate it's warming up at. And most of this residual uncertainty comes from the deep ocean that we're not measuring very well yet, but we're going to measure next. We're expanding our technology to measure the deep ocean. So how do we build up a picture of what's going on? One measurement, I keep talking about 1.3 million measurements. One measurement looks like this. Here's the surface, here's 2,000 meters, here's a profile of temperature, here's a profile of salinity. Quite a lot of variability near the surface, sort of slow trend as you go down the water column. So here you don't have to measure very often. Up here you've got to measure a lot to figure out what's going on. So that's one measurement made once, one of the 1.3 million. One instrument, if you, this instrument has run for about 10 years, and you've pieced together into this picture a lot of different profiles, several hundred, and then you colour it according to either the temperature or the salinity. So the colours here are salinity, and obviously in 2011 it got carried across into a place where the ocean properties were different. When you build up enough of those, you can start to build complete maps. So this is a map created by the UK Met Office using data from the floats. It's the southern hemisphere. You'll recognise Antarctica, South America, Southern Africa, and this is the temperature at 1 kilometre depth as measured by the floats, and these blues is about 0.7 of a degree, these yellows are about 5 degrees, so you can build up pictures of extremely remote places by assembling all these data. So what are the uses of the data? Operational uses, centres in Australia, France, Japan, the UK, the usual countries, assemble all these data to try and do forecasting. They're beginning to learn how to use these data for seasonal forecasts. How good will the monsoon be? And I'll mention that a bit more about that in a minute. And we're using it for the research. Climate change, global ocean heat content, sea level rise due to the thermal expansion of the oceans. So why is the ocean heat content so important? Basically because 90% of the global warming takes place in the oceans. That's what I said, the pink stripe is pretty damn small, the blue stripes absolutely dominate. The air doesn't weigh much, so it can't take up much heat. The land is very solid, so it's hard for the heat to penetrate. The oceans can move and mix, so extra heat can penetrate deep into the ocean easily. Here's an example of ocean forecasting. This is a vertical slice along the equator in the Pacific. So you have to imagine the West Pacific, the East Pacific, so this is Indonesia, this is Central America, this is the top few hundred meters, and it's coloured according to temperature, and there are warm colours and cold colours, and there's 2 plots in January and 2 plots in February of 2014. So these measurements were being made by our equipment and others, and what you can see is this warm blob is moving well over to the right, and by April it is well over to the right, and all the blue, the cool colours displaced, and there is a big warming anomaly in the Pacific Ocean. This enabled the forecasters to be able to forecast that that year there was going to be a significant El Nino event. An El Nino event is a huge climatic disruption that results in flooding in some places, droughts in other places, and data from these floats were able to forecast that an El Nino was going to occur so that governments could plan and be on the lookout. Let me just slide that across in order to jump across. So, as I said, if we want to study climate change, the modern Argo baseline makes change detection much more robust. So, if you want to say, how has the world changed from, say, 1950 to 1960 until now, 2000 to 2010, these were all the measurements in that 10 years. These are all the measurements in the present 10 years. So that's why the uncertainty line was very big. The dotted lines were very wide in the 1950s and 60s because we sort of got a reasonable guess of what the ocean was like. There are big swathes that we're actually just not sure. So we've got to say we're not sure. Now we are sure. We've measured everywhere, and in 10, 20, 30 years' time, we will be able to be absolutely sure and precise. We do know that the world's oceans are getting warmer, and there are distinct salinity changes as well. It's also the case that I've talked about warming and warming of the atmosphere. Actually, warming of the atmosphere is not a good estimate of global warming. For a couple of hundred years, it's the best we've got because those are the only measurements that were made. But now that we can make the ocean measurements, that should be the key. As I pointed out, the atmosphere is sort of an indicator of what's going on, but it's only a thin stripe in terms of the energy contained. So here is a time series from it's 1880 till 2010. So this is 1880 to 2010 of global average temperature as measured in the air. And you can see in the last 10 years, it wasn't going up very much. And there was much talk in the press of, oh, global warming's not happening. There's a hiatus, there's a stop in global warming, it's not happening anymore. And that was based on looking at the air temperature. Whereas actually, this has fluctuated and gone up and down, the underlying trend is still up. But this is only 10% of the global warming energy. Here is what is happening actually in terms of the planet warming up. This is now the ocean record from 1960 till the present. And all through that 10 years, when this is precisely the 10 years where we were measuring it very, very carefully, it was getting warmer at exactly the same rate as it's always got warmer, as it has to be. Physics says if you've got all that carbon dioxide in the atmosphere, it has to trap the heat. You simply can't beat the physics. So the fact that there was a little bit more in the ocean and a little bit less in the atmosphere wasn't actually the key point. It was absolutely nonsensical to say global warming is off for the time being. Global warming was very much happening. So that was illustrating that. The only time where air temperatures and ocean temperatures do sometimes drop together is during a major volcano event. So Pinatubo, El Chichon, big volcanic events, they put so much dust in the atmosphere that actually acts as a barrier. It's like painting a greenhouse windows white. It just keeps a lot of the incoming radiation out. So sometimes during big volcanic events, everything cools down. But that is simply a blip on the underlying trend. Just skip the next slide, and I'll say a little bit about salinity. So why is ocean salinity important? What we'd really like to know about is ocean rainfall. So, as I said, we've got this thing called the hydrological cycle, fancy name for the fact that nearly all the water that evaporates, 85% of the evaporation of water is over the sea, and most of it falls back over the sea. Some of it evaporates over land, some of it falls back over land. And what everyone wants to know about is the net result of this amount coming out of the sea and falling back on the land, because that is what's critical for droughts, floods, agriculture, and everything of that nature. It's very hard to measure everywhere the amount of rainfall and the amount of evaporation, but where water evaporates, the ocean left behind is a little bit saltier, and where it rains, the ocean becomes a little bit less salty. The concentration of salt goes up or down. So if you measure the concentration of salt, you can discover where there's lots of evaporation and where there's lots of rainfall. So this is a map of the average ocean surface salinity. The colours exaggerate the fact that the darkest blue is about 33 and the darkest red is about 37 parts per thousand. So we all know that the seawater's salty, but the surface Atlantic is a little bit saltier than the surface Pacific, for example. It's about 4 parts per thousand different. And this is a map showing where the ocean tends to evaporate. So the red here indicates evaporation. So lo and behold, the North and South Atlantic evaporate quite a lot, and lo and behold, the North and South Atlantic are quite relatively salty compared with most of the world's oceans. If we now look at changes, so here's the same map. The North and South Atlantic are salty. This is now the trend in saltiness as measured over a long period. And what you discover is that where it's salty, it's getting saltier, and where it's not quite so salty, it's getting less salty. So this means that this process of evaporation and rainfall is speeding up. That's how we interpret this. The salty bits are getting saltier, the fresh bits are getting fresher. And what that means in land is that the wet bits are going to flood more and the dry bits are going to get more droughts. Because this whole process of evaporation and rainfall seems to be speeding up. So just a summary so far, and then a couple of minutes at the end on where we're going next with Argo. So, observing and understanding the ocean's interior is critical to understand global warming, sea level rise. I haven't spoken much about that, but I can do afterwards, and the water cycle. The unprecedented capability that we have enables us to detect changes sooner and with greater confidence. Autonomous platforms are now absolutely the dominant source of data for describing the ocean. We've already done more than twice as much as the whole history of other observing. And we're going to extend Argo into the deep ocean and into making other measurements. So just, I'll just do one picture of deep floats. For the first 150 years of ocean observing, if you wanted to get into the ocean, you had to have one of these, and you had to have people on it. This is the new RRS Discovery, which is based here in Southampton, set off to the Southern Ocean a couple of weeks ago. You may have seen it on the local news. The way you can now get to the deep ocean is one of these. The tube design that I showed you before, if you wanted to get down to the full ocean depth, where it's 600 atmospheres, the tube design will let you down. You have to make the walls so thick that it'll be too heavy to float. So you've got to go for a sphere design, because a sphere is a more advantageous shape. So floats to go past 2 kilometres down to 6 kilometres are made of spheres, and the material we use is glass. Because surprisingly, sort of not counterintuitively, a glass sphere with a wall of about 1 inch thick is perfectly capable, if perfectly made, perfectly capable of withstanding 600 atmospheres of pressure, because the sphere is such an advantageous shape. If you could mill them out of metal, that would be fabulous. If you could make them out of titanium, but milling a sphere out of a block of an ingot of titanium would be a couple of $1 million per float, and you can make glass spheres for a couple of $1,000. So they're glass spheres made in 2 halves. So the yellow plastic here is just a builder's hard hat to hold them together and prevent them being scratched and knocked. Made in 2 hemispheres, pushed together with some sealant, and then all the batteries and instruments are inside. Here's our iridium antenna, here's our sensor payload on the outside, and this metal frame is just a stand, and when we put it in the water we just lift the whole thing away and just put that in the ocean. So, deep Argo, what we're calling our deep measurements. So this is getting to the bottom half of the ocean. How ready are we? Well, deep floats are being developed and tested by several groups. A new instrument package is under parallel development. It's also got to be able to withstand higher pressure, and the demands of accuracy are about a factor of 10 more demanding in the deep ocean than they are in the upper ocean. We've got to have an instrument that will measure ocean temperature to about 3 millidegrees accuracy for 5 to 10 years unattended without electronic drift. It's pretty demanding stuff. But our regional pilot deployments are proving technology, refining our estimate of the cost of doing it, and informing a global array design. Now, we've recently been asked by the G7 nations' science ministers to come up with a proposal for what a deep measurement program would be, and how much it would cost. It would cost about $25 million a year. So the existing program cost about $25 million a year, and to measure the other half of the ocean would cost another $25 million a year, which sounds like a lot. But if you divide it between 7 or 8 major nations, it's a couple of $1 million to actually answer the question, how much global warming is happening? How much would it be worth to our nation to know exactly how global warming is working and where? Is it worth a couple of $1 million for the UK to put in that funding? And I like to think the answer is yes. I'll just jump to the summary slide. Progress in many areas of endeavour, and oceanography is no exception, really follow from developments of accurate and cost-effective new technologies. Suddenly there's a new technology, and suddenly you have the ability to do things you couldn't do before. In the last 20 years or so, Argo's revolutionised our ability to collect temperature and salinity data from the oceans. It's the only technology able to provide global year-round coverage. Over the next 10 years, it's likely to move into deep and also biogeochemical measurements, oxygen, ocean acidification, things like that. It's the key data set for global change studies. I think what's particularly exciting to me as somebody who works in the Oceanography Centre where there are students, is that the young scientists of today are going to be the first generation who will actually be able to describe human impact on global climate completely and without doubt. So I think the generation that we're in has developed the technology to make the really comprehensive measurements, but we need to do that for 30 years, and then the next generation of scientists will actually be able to describe with very narrow uncertainty what's going on. So I'll stop there. There'll be a break, I understand, and then a chance for questions for people who want to ask questions. Thank you for your attention.
Just 10-minute break, comfort break. Anyone not on the list?
Your instrument has dropped.
Yes.
You showed it, going along.
Yes, up and down. And
Yeah,
across,
yeah, but you only take the measurement when it actually drops.
We actually measure on the way up.
On the way up, right.
So we do make measurements. Well, actually, we make measurements the whole time, just because scientists will always make as many measurements as they
might as
can.
well, if you can.
But the crucial ones are on the way up.
Right.
So when you've dived to maximum depth, you come up to the surface, and that's when you can send the data back.
Yes,
because you've got the
of course,
satellite.
obviously, yes, yes.
So the most useful data are the ones collected most recently.
Yes.
So the weather forecasters don't want to know what it was 10 days ago when you were drifting. So the climate scientists like me are interested in the data all the time you're drifting. But the really crucial stuff is just collected in the last 6 hours before you're on the surface, and that means the stuff while you're rising.
Right.
So-
And the sea is warming up. Is this at the top more than the bottom? Or,
Well,
or do we not know this?
I was just saying that the picture
Oh,
up there.
right.
I was just describing.
Sorry. Yeah.
That's all right. So this is a kind of a complicated picture, but basically it goes from 60 south to 60 north. So basically this is Antarctica, and this is getting up to the Arctic.
Right.
And here's the surface, and here's 2 kilometres depth.
Okay.
So it's a big sort of north-south
Yes,
slice.
yeah.
And all the reds and yellows are warming, and all the blues and greens are where it's cooling.
Cooling, yes.
So, for example, if you go the left-hand quarter, so this is a latitude of about 30 degrees south.
Right.
So basically, everywhere south of the continents, everywhere Africa and south of that, South America and South Australia, that is all warming up,
Right.
all through the depth. It's warming up everywhere.
Right.
There are some places in the North Atlantic, particularly, it's warming up quite a lot. Some places it's sort of a mixture of yellows, greens. It can't make up its mind. It's just. But the warming is certainly not uniform everywhere.
No.
And that's why it's really important to measure it.
To measure it, yes, yes.
And this is why it's a bit of a problem that until we started making measurements in the southern hemisphere in winter,
Yes.
all those pictures of what was the temperature in 1950.
Yes.
Well, frankly, we only had that half of the picture.
Yeah.
So when we say how's it warmed since 1950, what we're really doing is averaging all this and saying, it's a sort of mid-yellow.
Yeah.
So we think since 1950, we think it's sort of warmed up by this many degrees. Actually, we do not have that part of the picture. So that's why we need another 30 or 50 years, and then we'll really know.
And also, I was very shocked about we know that global warming is increasing.
Yes.
But the rate at what it's increasing now.
Yes.
And you think that we knew about this problem in the 1800s.
Yes.
Such. Why nothing's been done about it. I mean, I remember that I actually was brought up in Isleworth Hospital, so
Right.
roughly around
Yes.
Heathrow Airport. And I can remember when the Clean Air Act came,
Yes.
which is why I guessed at the early 50s.
Yes.
Because I thought that was only a recent thing, But it's amazing how much it's still going up. So global warming.
Yes. So I
when
think
we
the reason,
know
the
that there
reason
is
it
a
wasn't
problem.
really, the reason it wasn't really taken seriously.
We're not doing enough.
The reason it wasn't really
I knew
taken.
that, but
if we find this.
it's even worse than I thought it was.
So I think this picture has.
Yes.
So the as I said, the guy in Arrhenius in 1896,
Yes.
he said, what if the carbon dioxide doubles?
Yes.
That would make a big difference. The Earth would warm up by 4 degrees.
Yes, yes.
So he worked that out as a theoretical construct.
Of course.
At that stage, nobody dreamed the carbon dioxide could ever double. Right, so the value then, the atmospheric concentration was about 280.
Right.
So here we are, 1960, it was up to 320.
Yeah.
So even by 1960,
Yes.
atmospheric carbon dioxide had only gone up by 20%.
Yeah.
So people saying, if it doubles, it'll warm up by 4 degrees. People say, but it won't double. How could it ever? How could
Yes.
mankind ever burn that much? But
Pretty
this
good.
is just, so now we're up to, we've now gone up to 400. So we started at 280.
Yes.
We've added 50%. Mankind has added 50%.
Yeah.
So we're halfway to Arrhenius' doubling.
Yeah.
So another 80 years, and we would have
It might,
completed
it might not
Arrhenius'.
even be as long as that, because
Well, it
the fact
depends.
that your base thing is hotter than
It-
and more, you know.
Well, and there are lots of other considerations,
Exactly.
but I think
Yeah.
you know, all through the 80s,
doesn't necessarily go up.
When I was you know, a young scientist
It's going
in
up
the 80s,
higher that end anyway.
it's
on the
getting
right.
steeper and
It's
steeper
much
and
steeper.
steeper. Yes, it's
And I
getting
think that would be
steeper
right
and
because it's almost like an imploding thing, where
So
you've got
yes.
the heat there that's already causing a problem. It's adding to it. Turn all the lights off quick.
Yeah, so this is
Yes, that's
this is how it's
shocking,
been.
that.
It's
Yeah.
you know it's since 1800.
Yes.
It was sort of slow. So about here,
Yeah.
you know, when we were all youngsters,
Yes.
and some of us weren't more yet.
Yes.
People sort of said, well, we're only at this part of the curve. You know, if we go out here, it'll
That's
take
right,
it'll
yes.
take 200 years before
Yeah.
it's accomplished.
Yeah.
But
It's
actually,
got much steeper.
It's got, and it's getting.
And we know
steeper
about
still.
it. And we're
Yes, and
using
now- and now we
alternative
know that.
energy.
Yes. But the population has doubled. So of course the amount of energy
yes,
we need
of
has
course.
doubled as well.
We need more wars and things.
Yeah.
There must be an interesting correlation with the type of energy being used, because since I was at university, coal has gone like that.
Yes.
There was a huge spike, wasn't it? in
Well,
natural gas.
coal has gone like that in the UK, but of course it hasn't gone like that globally.
It's certainly
You know,
not the dust.
China is digging up coal as fast
Yeah.
as it can to make steel.
So it's
You know, the
relevant.
US has just said we want to revive our coal industry.
So the UK is irrelevant, really, isn't it?
Well, it's irrelevant in the sense that whenever you go out to an election and vote, your vote is irrelevant unless the margin was 1. You say your vote's irrelevant, but if everybody says that, there's no votes. So we're relevant in the sense that we are one of 10 or 20 countries that contributes to this problem. So you only solve it if everybody agrees to solve it. Like you only get a government when everyone goes out to vote.
Well, clearly, natural gas and oil is, say, 65, 70.
Yes, very much. Yeah, very much. Very much so. Very much so. But yes, I think the amount of energy from coal is probably just as high as ever it was because China used so much coal these days. You know,
You
China did
mentioned during your
that
talk about interesting about dust being
Yes.
ironically, I use the word ironically, perhaps working in the favour, because
Yes.
at ground level you don't quite see it that way to deal with.
Well, so curiously, there's been a lot of talk about what they call geoengineering. Would it be possible to do things to the planet to reduce global warming? And people have said, well, we could try and put giant turbines in the ocean to pump heat quicker into the ocean, so the ocean absorbs the heat quicker. You know, and giant stirrers to get carbon out of the air. But one of the proposals, which I thought sounded like quite a good one, is that you could experiment with trying to spray dust in the upper atmosphere, and create a shield in that way. And the advantage of doing that as an experiment is it's utterly reversible because the dust will only stay there a year. You know, if it doesn't work out, it'll just fall out with the rain, and you get that. You know, that's been a natural experiment with volcanoes. The 2 or 3 big volcanic eruptions that I mentioned, Pinatubo, El Chichon, and some others earlier on, the global temperature record noticeably cooled. They just pumped, 2 cubic kilometres of Earth up into the upper atmosphere as dust, and it cooled the Earth down for a couple of years. And then after a year, it washes out.
It's a temporary solution.
It's a temporary solution, but it's an experiment you could do that is utterly reversible. What you don't want to do is go and paint all the fields white or something and have it difficult to reverse.
Do you not think there's also of any real danger though if somehow you got that allowed, you would be enabling the people who just want to then carry on.
Absolutely. It would, yes, by saying, oh, the climate problem's now fixed, carry on as you were.
Yeah.
I mean, that would be. But I mean, geoengineering is a totally different, not my field really. But some geoengineering solutions do appeal as things to experiment with.
But related to that, with use of coal and energy production, with something that's come in on a fairly large scale is scrubbing sulphur out of the emission, and also low sulphur coal to start with.
Yes.
But ironically, is that part of your little blip on your graph, and that it's going the other way? It's removing these sulphurous.
Well, the real trouble is it's not. No, I mean that's had no. If you look at this part, of the curve, I'm afraid the CO2 is still going up just as fast as it ever was. It may be that after a period of getting steeper and steeper, it might just be going up.
I'm thinking of the volcano effect. That if you put these sulphurous
particulates up in the higher atmosphere,
it's like dust effects.
I mean, the real I don't think it's being done on a big enough scale for that to be noticeable, to be perfectly honest. I mean, when people talk about emissions controls, what they talk about is freezing emissions at the present level. So if that was to happen, this curve would suddenly become horizontal. And it's just nowhere near. It's not even tailing off. It is still. It might just be going up at the same rate or slightly steeper. It's certainly not suddenly tailed off. The idea was by 2020 our emissions would not be going up anymore.
It's not going to happen.
You just cannot see that is tailing off any time.
While on CO2, there's absolutely no dispute, arguments amongst scientists or anything about the measurement in 1960, how they measured the CO2, the equipment they used. That's absolutely stuck.
Yes.
There's no dispute amongst anyone about that.
I mean, inorganic chemistry was all stitched up in about 1920. This wasn't a sort of, I've invented a way to measure CO2 concentration in the atmosphere. They could do all that 100 years previously.
I'm thinking compared to global sea level rise, and that there's an Indian system that basically relies on tide gauges, and there's a satellite system. And the two don't really agree together, and
that's to do with where the zero is. But that sort of inorganic gas chemistry. As I say, Tyndall in 1850 was able to say, I will measure what they call the radiative properties, the ability of various gases to transmit energy in different wavelengths, and he did that in 1850 perfectly satisfactorily. Because that sort of mechanical stuff they could do. They were perfectly capable of having sensors and deciding how much CO2 there was. And the reason they could do it so well is they would calibrate their sensors by making mixtures of gas. So they could make a gas, they could get pure nitrogen, which they knew how to make, pure oxygen, which they knew how to make, pure carbon dioxide, which they knew how to make because they've been able to make it for 150 years. I mean, when did Priestley do oxygen? I mean, back 1780 or something. And they could make a mixture of different ratios and say, we know this is 20%, this is 10%, that's 5%. So you could put the sensor in that, and then you could put the sensor out in the air. And if these were uncertain measurements, they would be very noisy. These are just, they'd be all over the place and get better and better.
And you'd have a funny edge where the measurements got better as well.
But no, that measurement is. I mean, I would say this is 19th century chemistry, not even 20th century.
But the annual up and downs look so precise; they look a bit bogus.
That's just because. I think that's just the change in the seasonal cycle.
Very precise and regular.
But I imagine that's driven by the seasonal cycle of temperature at the top of the Mauna Loa Observatory. The different temperatures will have slightly different particle constituents.
It's not to do with the Northern Hemisphere bias in the growth of the forests.
It could be. I mean, I think things are... The Northern and Southern Hemispheres are not identical, but things are pretty... I think the whole point of doing it here is it's very well mixed. You're not just downstream from Los Angeles, and every winter they stick the heating on, and suddenly something happens. This is up in the reasonably high atmosphere, 2,000 miles from any industrialisation. So I think there's plenty of time for whatever's going on and whatever's driving this to have mixed it well up. Well, that's why it's so regular, because it's a big average rain.
The ice is disappearing, and apparently methane is given off.
Yes, yes.
Even the permafrost is melting, so
yes.
it's quite considerable amount of heat. I don't know whether this is just locally or whether it's generally.
Well, I think the problem with the methane is that the methane molecule is so much more effective as a greenhouse gas than the carbon dioxide molecule. So I think one of the pictures that I showed, this one I think, showed so that the size of the wedges in this pie chart are in proportion to their effectiveness as greenhouse gases, how much greenhouse effect they have. And methane gets about an eighth of the pie there, but it's only a tiny fraction of the gas, but methane is so much more effective. So at the moment there's lots of methane basically frozen into the permafrost, into the tundra, and that sort of thing. And the risk is you only have to heat it up a little bit. You don't have to. It doesn't take much heat to melt it out, and then it becomes a gas, and then its effect in terms of trapping heat just becomes hugely out of proportion to the amount of energy it actually took to melt it.
The other thing I'm rather curious about is that during the Cambrian period, the parts per million of carbon dioxide was 400.
Right. Yes.
So
indeed. So yeah.
Where did that disappear?
I mean, this was the last 10,000 years. I guess the Cambrian is about 3 billion years or thereabouts. So as I say, the amount of carbon dioxide has always fluctuated up and down, and it turns from forests into atmospheric carbon dioxide. It can get buried in the ocean. All the stuff that turns into the oil. So basically, that is all stuff that grew as marine life. Grew as crustaceans. So as crustaceans busily grow their shells in the seawater, they take carbon dioxide out of the seawater and therefore out of the air. So the crustaceans grow their shells, that takes carbon out of the seawater. That means the seawater concentration is below saturated, so it goes in at the surface. So it's drawn down and then falls into the sediments, where it has sat for the last couple of 100 million years until we've dug it up and turned it back into atmospheric. So indeed, this has fluctuated between probably 200 and 400, and we've fluctuated between most of the globe being frozen and most of the globe being tropical. That has fluctuated, but the point is it hasn't changed. Those fluctuations have taken tens to hundreds of thousands of years to grow slowly, and this happening in 100 years is not a natural cycle. But people have said, well, perhaps we need to get it back into the sediments. So they said, if we can make the oceans grow plants quicker, then the crustaceans will grow quicker, and then they will die and they'll fall to the seabed and take the carbon with them. So there means
but massive areas like the Barrier Reef are all being destroyed at the moment.
So that's a separate thing.
Yeah.
Partly to do with the things that upset marine life are either warming or acidification.
Yes.
And corals are susceptible to both of those.
Yes.
So anything that makes sort of calcified shells, anything that's got calcium carbonate in, which of course is where the carbon gets buried, they don't like it if the oceans are. People talk about ocean acidification. The oceans are naturally alkaline. They're more alkaline than pure water. So when you talk about ocean acidification, what you actually mean is you add carbon dioxide and they become not as alkaline as they used to be. So in terms of chemistry pH, where 7 is neutral, the oceans are naturally about 8, which is on the alkaline side, but they'll go from sort of 8 to 7.5. So they'll still be a little bit alkaline, which is favourable for making these carbonate things. But in order to grow a good carbonate shell, you need it to be pretty alkaline. And if it's only a bit alkaline, it's much tougher. You grow damaged shells, you grow softer shells, and then you fall.
I was coming from the theory about this being able to grow more plants and get more crustaceans, and yet we can't stop this from being destroyed. And there is a lot of talk about, I think it's a lobster or something that eats something that normally eats.
Yes,
because it's very complex. We can't say it's one thing.
The temperature changes and a new species comes along and it eats all the polyps out of the coral and slaughters the coral, which don't do terribly well when it's warmer anyway, because they like it a bit on the chilly side.
But I'm saying we can't even...
Yes, see the barrier reef while you can, because it will be gone in 100 years or something.
Can I ask a question about floats again?
About
your Argo float?
Yes.
How do you stabilise, when you're out in very, very rough seas,
yes.
Right, how do you make sure that they're, for example, the right way up?
Ah.
And how do you calibrate the instruments? How do you know the operational ones haven't been damaged? What do you compare them against?
Or eaten by a whale, that's what I don't know.
And how many are hit by boats? That's what I want to do.
Very few.
I'm surprised.
And if one was hit by a boat, we wouldn't necessarily know. We'd come off worst. The boat would survive, we wouldn't.
But there might be a big hole in the boat.
No, because we're small, we're light.
Okay.
That's
all right, don't carry on.
How do we keep stable? So we put this little disc here, which is just a plastic dinner plate, basically. And that helps keep it stable in the water. So when a wave comes along, it rides over the wave, because if the wave tends to lift, then it drags the disc and the float goes up and down. In terms of how we keep it upright, you put the batteries at the bottom, because they're the heaviest part. So the top part has got a little bit of airspace in where round the circuit boards and that sort of thing. So you basically just make sure that you put the batteries at the bottom and then it acts like a keel and keeps the thing upright.
So if it did sort of tumble over in a massive wave, would it self-right?
Then it would be self-righting because all the heaviest stuff is at the bottom.
Right.
So rather like a lifeboat, but they have a self-righting mechanism that's a bit different. It's simply got the heavy bit at the bottom, basically.
Have you got a record of how many have disappeared?
Well, we have deployed, over the programme, we've deployed just over 13,000, and there are 4,000 still active. So 9,000 are deceased since we started deploying them. Mostly, they will just exhaust their batteries. Some of them suddenly just disappear for no apparent reason. So if you know that we monitor, one of the things they send back, along with the ocean measurements, they send back engineering data, battery voltages, diagnostics about the instrument health. So you can watch the voltage drop off, and then it just doesn't send anymore. The battery's got exhausted. So that's that. Sometimes they just disappear for no apparent reason. That's very frustrating, because it's very hard to, when you don't get the object back, it's very hard to figure out what went wrong. Some of them wash up on the beach. 5 a year wash up on beaches, and then we try and get them back. Chiefly because they're a hazard on the beach. It's environmentally responsible to get them back. They're damaged beyond repair and use, but it's good to try and get them back.
A little tag on them that tells people that they're...
We do. We have a little label on which says if found. So they all have a number, and we have a clearinghouse. And basically there's a label that says, if you find this, contact this website. And then you send a picture, and you say, I found float, and it's got 27486 painted on the hull. And I get a phone call and get told, Brian, one of your floats has washed up off Indonesia. What are you going to do about it?
Go on holiday.
on the data transfer, how much does a single squirt of data into the Iridium system cost?
So that depends on who you are. So if you're the US float program, then they get their Iridium very, very cheap. So they don't worry about the telemetry costs, because it all goes through their Department of Defence, and they get their Iridium very cheap. We pay about £100 a month for each float. We pay £100 every 2 months. We pay about £50 a month for each float, and the UK maintains 160 floats in the water. So we're paying several thousand a month for our telephone bill.
Each squirt is just a couple of seconds?
It's a couple of minutes. So we send about 30 kilobytes of data back each time the float comes
And
up.
that's every 9 days?
Every 9 or 10 days. So 3 times a month we send it. We have a couple of minutes. Sometimes it takes a bit longer. If the weather's bad and you've got a lot of waves washing over the antenna, you might drop the connection and have to start again.
So It's quite a low data rate, but it's very reliable.
Yeah. I mean, I can't remember what the connection speed is. It's probably 9600 or 19200 or something like that on the modem once it's made the link. I mean, the Iridium people are always trying to increase the data rate. Yeah.
You mentioned at the beginning Jason satellite.
Yes.
Tell us about that.
Okay, so Jason, right, so the Jason satellite, there had been in the 90s satellites built to measure sea level. So trying to address the question of what is sea level rising? If you do it just with coastal tide gauges, of course you know that the sea level is going up at the coast, but it might be going down somewhere else. So in the 90s, they started putting radar transmitters on satellites, what they call radar altimeters. And these basically were very, very precise instruments that the satellite would fly over, it would look down, and it would send out a radar pulse and measure the time to get to the sea surface and back. It would be reflected off the sea surface. And then if you know where the satellite was, to within a few centimetres, and you measure the time correctly, then you know what the sea level was to within a few centimetres. So you've got to measure the satellite up there, going at satellite orbital speeds, to within a couple of centimetres, and the round-trip travel time. And there were a series of satellites that did this from the early 90s onwards, and they typically lasted about 10 years. And so at about the time that Argo was starting up in about 2000, the next one of those sea level satellites was coming along, and it was going to be called Jason. So we thought Argo would be a very appropriate marine counterpart, because the Jason satellite was tackling the very similar scientific question of how fast is sea level going up. And something that I didn't talk about but could have is one of the reasons we're interested in the ocean temperature because of the global warming problem. But about a third of all sea level rise comes from expanding the ocean by warming it. So sea level goes up because if you melt the ice and the water runs into the sea fills up. But about a third of all the rise is simply warming up what's there. So when you warm water, it doesn't expand very much. But if you take a 4-kilometre pile of water and warm it up by 0.5 degree, then it expands by 0.1%, and 4 kilometres, that's 4 metres of rise, or whatever. So measuring ocean temperature and the thermal expansion is about a third of all the sea level rise. So our programme is geared to that problem, as well as just, is global warming happening and where's the heat gone? It's critical to understand the ocean warming for the sea level problem. So we work very closely with the satellite sea level people.
I have a separate, unrelated question, and it might be a bit unfair. How do you cope with marine growth on these things?
Oh, well, no, that's a very pertinent question, actually. They spend most of their life submerged, quite deliberately so. That's why when they're not busy making a measurement, we don't need measurements every day, every 10 days is fine. They park at 1,000 metres where it's cool and dark, and marine growth is not a problem where it's cool and dark. However, when they visit the surface, marine growth is a problem. So, in our sensor payload, growth inside, the measurements are made, we have a little pump, we have a duct, and the sensors are in the pumped duct. And if you get growth inside the duct, it's a real problem because it contaminates the measurements very badly. So they have a tiny pill of biocide in the duct that just slowly dissolves over a period so that you don't get growth inside the duct. And the biocide they use is called TBTO, tributyl tin oxide. Okay? This is what they used to paint the hulls of ships with. And it's now banned. This is a significant problem for us. It's banned.
Yeah.
Ships still do it.
Well, yes, but it's banned because when you paint a ship's hull and put on 25 tons of paint with TBT and it just dissolves everywhere, this is a problem. We have about 3 grams in each float. So we could run our entire programme for 100 years on less TBT than one ship hull painting. And yet, it has been banned, and we have had to apply, the manufacturer has had to apply for an exemption all the way up through the various departments. So I wrote a letter of support saying, A, this is critical for climate science, and B, the amount of TBT in any single float is so minuscule that it should get an exemption, that we should be allowed to continue to do this. Coasts, and it's, as I say, we could run the whole programme for 100 years on the amount of TBT it takes to... But it just got sucked into this. So that for a while the rule was that you could not import TBT to the European Union. But fortunately they had a big stack of these pills, 10 years supply of these little TBT tablets. The manufacturers have now sorted this out. But there was a risk that they would have to ship us the instruments without the biocide, and we'd have to then add the biocide ourselves or something like that. Because they were,
if you have any left over, can we have it for some of our votes, please?
I don't think, I think if you took the entire programme supply for a decade, you might be able to crush it up and get enough to paint it.
Was this an international agreement about TBO?
TBTO. I'm not sure who brokers
I
it.
have been told that a lot of the boats, bigger boats, still have it in their hull.
It's probably the case that they haven't had to scrape it off. It's probably that they won't be allowed to repaint it next time around.
Something comes from Korea or somewhere.
Yes, but if you're but a coastal state would probably have the right to deny entry to the port of a boat that's not conformant to some. Usually with these new regulations, it comes in first for new build ships, and then existing ships get a period of grace to, and usually about 10 years or something, they get a period of grace to catch up.
Question in the back here.
Oh yes.
Do you let them change the batteries and put them back out?
We don't. I'm very frequently asked that question because it's a very good question. For one thing, when the float, the most likely time that the float will fail is when the controller switches on and says time to inflate the bladder and come to the surface. That's the biggest energy demand. So they will die not at the surface. So if you said you wanted to pick them up, you'd have to say, well, I will simply tell them to abort their mission and go into fixed surface mode, 80% of the way through their life or something like that. And we thought about doing that over the programme. But the both financial and environmental cost of picking them up would be enormous. So when we put them out, we can put them out on a merchant ship or one of our research ships that's doing other research projects. We just put them out. So they all go out in straight lines. Very soon, they are essentially random. So to go and pick a float up, if you knew that a float was on its last legs, it was time to pick it up, that would cost at least a day of ship time. Because they're 300 miles apart, and a ship goes 300 miles a day, every float you pick up will cost a day of ship time. Now, the sort of ships that can go to the South Pacific and pick up the floats, they cost $20,000 a day, or $30,000 a day. So that would be the cost. It would cost as much to pick up as the whole float cost. But environmentally, that ship also burns about 6 to 8 tons of fuel in that day. So environmentally, to say we're going to pick this float up is going to cost you 6 or 8 tons of carbon every time you do that, which is just environmentally pointless. So in terms of, so eventually most of the float will simply dissolve away. So the float hull for these ones is aluminium. Aluminium is massively abundant in seawater. There's a huge amount of dissolved aluminium in seawater. It is simply not a problem. The bits, there are a few bits of plastic. This bit is a plastic cowling. This is a plastic disc. This is a plastic housing on the instrument payload. There's a few flecks of paint. There's some electronic circuit boards. There's batteries, but even the lithium in batteries, which if you have it in your bath is pretty damn horrendous hazard. There's plenty of lithium in seawater. It's only 1 part per billion in seawater, but by the time you dissolve 1 battery in a cubic kilometre, it's fine. So really, almost everything, if it just dissolves away, it's really not a problem. The only thing we're actually a bit worried about is the plastics. Because, as people are now realising, plastics don't dissolve, they simply break up into tiny particles of plastic, and that's, Well, so this is one of the things we need to engage with the manufacturers, is whether they could reduce the amount of plastics to reduce that. But all the rest of it, as I say, even things like the batteries and the circuit boards, the materials, when they're dissolved so dilute, all those elements, all their trace elements. I mean, there's even lots of gold. So I'll finish with a story. What's the time? It's almost time to. Can't see my watch now. Almost time to go. Right, funny story. So I referred to the Challenger expedition as one of the first serious organised marine science expeditions, and that was in the 1870s, and it went around the world. One of the next ones that was a seriously organised expedition was a German expedition in the 20s on a ship called the Meteor, and some German scientists wanted to go and survey the South Atlantic much better than the Challenger had done. So they wanted to go to the German government and say, you must give us a ship and we will go and survey the South Atlantic and we will measure the temperature and chemistry, we'll measure all kinds of chemistry about the South Atlantic. And the government, of course, wanted to know why the German government should put money into this. And the German scientist who was trying to organise this in the 20s, he said, the South Atlantic has got 2,000 tons of gold dissolved in it. And we ought to go and survey the gold concentration and find, it's only 1 part per billion everywhere. But he said, we will survey the concentration of gold and find where all the gold is in the South Atlantic. So he was told, well, you better get to it then, what are you still here for? So they went out, they had a fabulous oceanographic research expedition based on this specious idea that there was thousands of tons of gold in the ocean, which is absolutely true, it's just not very easy to recover. But and that will be the fate of all our lithium and all our aluminium. It will go the way of the gold that funded the Meteor expedition, and that was the first opening up of major ocean research in the 20th century. So there we are. Anyway, it's probably time to. If anybody else wants to ask questions, do. But it's probably time to release everybody from the seats.
Thank you very much.
You're very welcome.